Imagine a fluid moving in a complex but highly structured way, following a helical path similar to a corkscrew or a spiral staircase. In this scenario, the fluid is simultaneously swirling around a central vertical axis while also moving steadily upward at a constant speed. Measuring the flow, mass flux. To understand how this fluid moves through space, we can measure its mass flux, which is essentially the rate at which the fluid passes through a specific gate or surface. Depending on how we position these surfaces, the amount of fluid passing through them changes. The top gate, disc, if we place a flat, circular disc at a certain height, the fluid flows through it consistently because of its steady upward motion. The sidewall, cylinder, if we imagine the curved side of a cylinder, the fluid never actually crosses this boundary. It simply swirls along the inside of the wall without ever pushing through it, resulting in zero flow through this surface. The radial slice, phi plane, if we place a flat surface that extends from the center to the outer edge, like a slice of pie, we find that fluid passes through it as it rotates around the central axis. The constant volume. Incompressibility. An essential characteristic of this specific flow is that it is incompressible. This means that the fluid does not expand or compress as it moves. Its density remains perfectly uniform. A helpful way to visualize this is by tracking a tiny cube of fluid as it travels. As the cube follows its spiral path upward, it might tilt or experience shear, changing its shape slightly as it navigates the turn. However, a simulation of this motion proves that the total volume of the cube remains exactly the same at every moment. This constant volume is the physical signature of an incompressible flow. The internal spin. Vorticity. Finally, we can look at the vorticity of the fluid, which describes whether the fluid is spinning as it travels. In this helical flow, the fluid is undergoing rigid body rotation. This means that if you were to look at a tiny particle within the fluid, it wouldn't just be moving along a path. It would also be spinning around its own center, much like a solid object would. A visual demonstration of this shows a constant, upward-pointing indicator, representing the spin, that stays fixed in direction even as the fluid element itself spirals upward. This confirms that the flow is inherently rotational.